Okay, we're in section 10 of the notes. We're going to be covering the material. You should also be aware we're going to have also another exam being scheduled, and you should receive information on that if you have not received it already. So the bottom line here is that make sure if you haven't done it already, you want to get that honor code in. But once you do it, there's no need to put it in again. It applies to the entire semester, right? I think the majority of students have actually submitted their honor code already. But if you have not done so already, please do so. How do you do that? Click on this. It'll bring you directly there. All right. If you're having issues for some reason, you need to reach out to me. Please come by during office hours and we can discuss that. All right. So this section over here is going to be, exponential and logarithmic equations. Some things I want to point out to you, and again, I'll go to the whiteboard later, but there's a difference between an exact answer and an approximate answer, and certainly we'll go through that. For example, in Math 100, if you're given this equation over here, this would be the exact answer to it, that x would equal plus or minus the square root of 2. If someone said, could you approximate it? That's when things get a little bit fuzzy. How do you want me to approximate it? And then we need to specify the level of accuracy. Now, for example, over here, the square root of 2 is approximately, that's what that symbol here means, minus 1.4. All right. So someone says, well, could you get more accurate than that? Of course I could. You could get very accurate with it. Like over here, I'm out to 6 decimal places. Could you go further than that? Of course you could, right? You can do 100,000 places if you want to, but let's be reasonable. We need to pay careful attention to what's being asked in the problem. Do they want the exact? Do they want the approximate? If they want the approximate, how precise do they want that approximate? Generally speaking, they'll say to the nearest hundredth, nearest tenth, nearest thousand, 3 decimal places, 4 decimal places, yada, yada, yada. What we're going to be talking about, though, in this section over here is not stuff you learn in Math 100, but stuff that you're learning in Math 119, which is how to solve an exponential and how to solve a logarithmic equation. We will certainly go through examples, right? I do want to emphasize, though, in Math 100, you were given examples where you solved them, came up with solutions that may not have been true, and that's why we want you to check them. Now, why does that occur? We introduce what's called an extraneous solution to the problem by doing something that we shouldn't be doing, although we normally do it. And we'll talk through that at the whiteboard later. Then, of course, we're going to go to examples. As we go to the examples, we're going to try to illustrate the points we're trying to make over here. All right, let me go to the whiteboard and I'll talk through it. All right, so we're at the whiteboard now and I'll talk through the material. And again, I just want to point out, if you were given Math 100 problems and someone said to you, could you do that problem? Of course you could. For example, in Math 100, if they said solve for x and you were given x squared is equal to 2, there's a variety of things you could have done. I mean, you could certainly, use the zero product rule, but I want to point out, Math 100, you learn what's called the square root rule. So x would equal plus or minus the square root of 2. That gives me 2 answers. It says x could be minus root 2, or that's how that plus or minus is read, x could be equal to the root of 2. This was not an exact answer. And this is exactly what your teachers in Math 100 asked you to do. Now, the other thing they might have asked you to do was sometimes approximate these things numerically. And that's where things get sticky. We have to tell you. So for example, if I say approximate it to the nearest tenth, you would say, oh, minus 1.4. Yes, you're allowed to use a calculator to do that. Or x is equal to 1.4. This is an approximate answer to the nearest tenth, approximate. Nearest tenth. All right. So someone says, could you go on further than that? Yeah, your calculators are remarkable in what they could do. So for example, if you have a calculator, I mean, certainly you can go out to, really a large number of places, including Sage. Sage can go out to an arbitrary number of places. Like you could take it out to 1,000 places you want to. That would be really tough for someone to read, though. So generally speaking, we might simply say to the nearest 3 decimal places. Well, if I did that and my calculator was displaying this, what do I write down? Minus 1.414. All right. X approximately, it's an or, 1.414. That's 3 decimal places. If you want to go 4 decimal places, so forth and so on, you'd have to know how to round things, of course. Now this one over here, relatively simple. All right. So I'm going to say, know the difference between an exact and an approximate answer. Relatively simple concept. All right. Let's go to the next page. We're done with this one. And let's talk about how to solve an exponential equation. Now, I said there's a variety of ways of doing things, and we'll go through many examples. But the key here is that if you have an exponential equation and it says, some base raised to a power is equal to the same base raised to a power, what does this really tell me? It tells me x would have to be equal to y, which tends to be, or it should be, a simple thing to solve. All right, that's what we're looking for. Now, another thing to do is, let's say you're given something where they're not the same base, like you're given something up here, a to the x equals b. And someone's going to say, oh, I could write b in terms of a. You could, I'm not denying it, but just too much work. So what we recommend you do over here is to take the natural log or log base 10 of both sides. Let me write this down. So I'm going to take the natural log of a to the x, and that's going to equal the natural log of b. All right. Now, what am I saying? If a to the x equals b, the log of a to the x should be equal to the log of b. It should be the same. Now, what do we get over here? Well, the x comes down using the rules of logs, ln x, I'm sorry, I misspoke. ln a equals ln b. What's our intent to solve for x, our variable? What do you get? ln b over ln a. Now, let's say you don't like natural log, you want to write down base 10 log. And on your calculator, log is base 10. In mathematics, log is reserved for natural log, but you're not at that level yet, so don't worry about that. So if you did log base 10 of both sides, I'll write that down for you. And again, when I'm writing log in this classroom, that's base 10. Your calculator has that, by the way. What do you get here? X log a equals log base 10 of b. What do you do? Divide both sides by log base a. What do you get? Log base b over log base a. All right. Now, by the way, someone says, are they the same answer? Of course they are. All right. They're both the same. Your mileage may vary. You may say, I want to use natural log. I tend to use natural log because it's easier for me to write that down. All right. The next step is solving a log equation, which it shouldn't be that bad. You have these rules of logs, how to, condense and expand, yada, yada, yada. But the deal about this one over here, it basically, looking at it, it basically says, if you have the log base a of x and it equals the log base a of y, let me put out what I'm looking at. I'm looking at this thing here. What do they tell you? Well, if those logs are equal and they're both the same base, what does it say? Their arguments must be equal. And we'll be using that when we solve problems, right? We'll use that, all right? And no matter how bad these things look, we're looking for these generalized patterns, right? What do you mean by generalized patterns? We're looking for things like this. We're possibly looking for things like this, and other things, we're looking for things like this over here, all right? We're looking for it. We're looking for all three of those things. Now, someone can say, I see a problem that doesn't look like those. That's just not going to happen. They've got to look like those problems, all right? If they don't, we're going to spend some time trying to get it look exactly like those things over here. So what I want to talk about now is sometimes when you're doing things you're not thinking, which happens to a lot of people, myself included, and this happened also in Math 100. So for example, in Math 100, if you were given this equation to solve, and I'll go through the steps with you. What the teachers told you to do is to solve that. They had a method for it. And the method they had was isolate the radical. Well, the radical is isolated. And then they'd say, oh, raise both sides to the index of the radical, which is against square root. It would be a 2. And if you did that, you get something pretty simple. You get x plus 2 equals x squared. Then what would they say? They say you're in more familiar territory now that you're going to just try to solve that. And what would you get? Well, it's a quadratic. I would use a zero product rule. And what do you get over here? Well, let's write down. You get x and x. Generally speaking, they're pretty easy to do. And you get this over here. Let me just make sure that's true. You get x times x, x squared. Minus 2 plus 1 is minus x. That worked, and you do get minus 2. And what's the solution to this equation? It would be x equals minus 1 or x equals 2. A lot of students on the exam would box this, and then they'd get the exam back from the teacher, and the teacher would put a red mark through it. And they say, I'm sorry, that's the wrong answer. Let's go through why it's the wrong answer, though. And what do you get over here? The original problem is this over here. And what are we going to check? There's two things to check. One is we're going to check 2. We want to check it. I'm going to check this. And what would you get? Well, on the left side, you'd get the root of 4, and on the right side, you get 2. That certainly checks out beautifully. It works nicely. We're going to also check -1. What do you get over there? Well, -1 plus 2 is 1. Oh, that's not true, because the square root of 1 is 1, and 1 does not equal -1. So this is not true. So this is why the teacher put a red mark through it. All right. What is this known as an extraneous problem? Now, why did it pop up? If you square both sides of this thing over here, it would be a true statement. That's what we did, unfortunately, over here. We squared both sides. We introduced the extraneous answer. We have to account for that by checking our solutions. And this is going to come up with both exponentials and the log problems, where you're going to get extraneous answers which may not work. So you want to check them out. All right. So again, that's relatively simple, and I'm hoping you're able to follow that lecture material. Thank you.